Okay, so in order to do these related rates problems, it gives you a list of strategies that you're going to go through. Now, I'll go through the first couple problems without going through these strategies step by step, and then we'll start sort of referring to it. So let's look at this first example. What it says is the length of a rectangle is decreasing at a rate of 1 centimeter per second. So let's just actually underline that. The length of this rectangle is decreasing, so it's decreasing at a rate of 1 centimeter per second. So how we're going to write that is the rate at which the length is decreasing. So because we're doing rates, you're going to say dl of dt. So these are rates. The rate at which the length is decreasing with respect to time is equal to, it's decreasing at a rate of 1 centimeter per second. When you're decreasing, you're going to include negatives. Increasing would be positive. So this rectangle is decreasing at a rate of -1 centimeters per second. Then what it says is the width of the rectangle is increasing at a rate of 2 centimeters per second. So the rate at which the width of the rectangle is increasing with respect to time, so that would be dw dt. Because it's increasing, I would say +2 centimeters per second. What they are asking for is they want the rate of change of the area of the rectangle. So what they're asking for is the rate at which the area is changing with respect to time. This is what we're going to be looking for. And then what it says is it says find the rate at which the area is changing when both the lengths are 10 centimeters. So what that means is they want when the length is 10 centimeters and the width is 10 centimeters. Okay, so sort of here's what's happening. We have a rectangle and the length is getting shorter, okay? And the width is increasing. So it says like the length is decreasing at a rate of 1 centimeter per second. So my new length might be this distance, but the width is actually getting a bit bigger. So like this would represent a rectangle where the length has decreased, the width has increased. And then what's happening is the next rectangle, the length is going to get shorter again, and the width is going to get increased. So this is sort of what's happening with our rectangle. The length keeps going down and the width keeps going up. Okay, so the rectangle is changing. The length is going down by 1 centimeter per second, and the width is going up by 2 centimeters per second. And we want to calculate the rate of the area when the length and width is 10. So from here, what we need to do is we need to find an equation that relates length, width, and area. What's an equation that we could use that relates length, width, and area? Well, the area of a rectangle, what's the area of a rectangle? Length times width. So you want to have an equation that's going to relate these three variables. What's an equation that has length, width, and area? Well, it'd be the area of a rectangle. Once you have what your equation is, we're going to differentiate both sides with respect to time. So once we have, you're going to differentiate both sides implicitly with respect to time. So the derivative of A is 1. And then because you just took the derivative of A, we say dA over dt. So it's like, it would be 1 dA dt, but I don't need to have that invisible 1 there. So derivative of area is dA dt is equal to length times width. This is going to be a uv prime, so u and v. So it's going to be uv prime plus vu prime. So the derivative, okay, so it's u, which is L, v prime, the derivative of w is 1. And then whenever you take the derivative, remember when we're implicitly deriving, you're going to say dw dt. I just took the derivative of w with respect to time. So this would be u v prime plus v is w prime. The derivative of L is 1, and then you say I just took the derivative of L, dt. Okay, they want dA dt, like that's what we're looking for, so dA dt. How is the rate of the area changing with respect to time? So dA over dt is equal to, they want how is the rate of the area changing when the length and width are 10. So I'm going to substitute 10 in for L and 10 in for W. So I'm going to have 10 times dW dt. That was 2. dW dt is 2. Plus the width of my rectangle. They want to know when the width is 10. And dL dt is negative 1. So from here, dA dt is going to be 20 minus 10, and dA dt is going to equal to 10. Now, units. I'm going to show you next one how we're going to input units within the equation, but you say to yourself, this is an area question, and it was centimeters. So what would the units be for area if it's centimeters? Centimeters squared. Okay, so it's taking care of my area. Per, what would the time be? Per second. So what this sort of means is because this is a positive number, it's increasing. So the area of the rate at which the area is changing with respect to time, the area of this rectangle is going up 10 centimeters every second. That's what's happening. As it goes down by 1 centimeter per second, but the height increases of the rectangle, the overall area is going to change by 10 centimeters every second, is what's happening. Okay, let's do a volume question. The edges of a cube are increasing at a rate of 10 meters per hour. So here's what happens. We have a cube, you would draw your cube, and the side length of my cube, what are all the side lengths going to be for my cube? Yes, but if it's a cube, they're all the same, right? So because it's a cube and they're all the same, let's call this x, x, and x. So what it says is the edges of the cube, the edges of my cube are x. They're increasing. This cube is getting bigger, and they're increasing at a rate of 10 meters per hour. So this cube is like blowing up 10 meters per hour. So how you write that is dx over dt. This is how we write this as a rate. The rate at which x is changing with respect to time is equal to 10 meters per hour. How fast is the volume changing? So the rate that they want is the volume. So they want dv over dt. So how fast is the volume changing? This is what we're looking for. And we're looking for this rate when the side lengths are 5 meters. So I write when x is equal to 5. Okay, I need somehow to figure out a formula that relates x and v. Somehow I need to put these two in a formula. Well, let's think about what the formula for the volume of a cube is. What's the volume of a cube? Okay, so let's write that down. Length times width times height. Now change that according to what we have our length, width, and height to be. So what would the new volume of a cube be? Of this cube be? Length is x times width is x times height is x. So x times x, and Keel, what would that be? X cubed. So you need to come up with a formula that's somehow going to relate the volume with x. So I've done that. Once you have what your formula is, you implicitly derive both sides with respect to time. So we're going to implicitly derive both sides with respect to time. The derivative of v is 1. according to the power law, the derivative of x cubed is 3x squared. I just took the derivative of x, so dx dt. Now we say, what are we solving? We're solving dv dt, which is right here. And they want to know, what would the rate be? What's the rate of this cube changing, the volume, when x is 5? So now I could input that 5 for x, and I know what dx dt is. Dx dt is 10. So dt, oh, you guys, here's where I'll put in the units to sort of show you. You don't need units because a lot of you will be able to figure them out. Okay. So 3 is 5. Now it's 5 centimeters. So I'm actually going to put 5 centimeters. So it's when x is 5 centimeters. I'm going to square that. Oh, is it meters? Oh, yeah, meters. Okay, sorry, let me fix that. Meters. So this would be 5 meters squared. And then dx dt was 10 meters per hour. dv over dt. So 5 squared is 25. 25 times 3 is 75. 75 times 10 is 750. Now, the units, what you would do is you would say, okay, this is volume. Volume is always cubic, right? So it was meters, so it would be cubic meters, and time was hours. But here I had input the units to see that the units would work. So meters squared times meters, that would give me my meters cubed per hour. So what happens is this is a positive number. So what this dv dt means, the rate at which the volume of this cube is changing with respect to time, the volume is increasing at a rate of 750 meters cubed every hour, is what this means. Okay, how fast is the surface area changing? So how fast is the surface area? What they want is they want the rate. So rate is RD. So they want the rate of ds with respect to time. So this is what we're trying to calculate. When the edge lengths are 8, so when x is equal to 8, and they'd given me the other piece of information I could use from above was that rate at which x was changing. Because remember they said the edges of the cube are increasing at a rate of 10 meters per hour, so I'd need to include that. So dx dt is equal to 10 meters per hour. Okay, so this is x, x, x. We need a formula for surface area, and that formula somehow needs to have x's in it. Does anybody know what the formula for this cube would be? Yes. So Carly said that the formula for the cube, so the surface area of this cube, she said was 6x squared. So here's how she got that. The surface area of one of these sides would be x times x. So the surface area of one of the faces would be x squared, and there's 6 faces of a cube, 6x squared. So I just have to make sure that my formula relates these two variables, which it does. And if I actually look at this would be step 3 here. It says relate the known and desired variables using formulas. Okay. Okay. So once you have that, your formula, differentiate both sides with respect to time. So the rate at which the surface area is changing with respect to time, the derivative of 6x squared would be 12x dx dt. And I'm trying to find this. So the rate at which the surface area is changing with respect to time is 12x, and dx was 10 meters per hour. What's 12 times 8? 96. So the rate at which the surface area is changing with respect to time. Okay, so 12 times 8 is 96. 96 times 10, Sarah, would be what? Sorry, 60. And Sarah, what would my units be if it's surface area? That's right, meters squared per hour. So again, what that means is the rate at which the surface area of this cube is changing is it's increasing, because it's a positive number, at a rate of 960 meters squared every hour. Okay? Now, we're going to do the same types of problems, but I'm going to introduce one new thing, which is we haven't talked about number 4. So number 4 in the strategies for solving is sometimes you're going to get problems where something is, it's called a fixed variable. So something is not changing. Now on the cube that we just did, like when this cube was getting bigger, there's nothing fixed on this cube. I'm going to show you an example of something that wouldn't change. So I want you to imagine this. You have an aquarium, length 70, width 20, and height 50. So put those 3 units in. Your length is 50. No, sorry, length is 70. Width is 20. So we've got 70 centimeters. This guy is 20 centimeters, and the height of this is 50. So this is an aquarium, let's say you have at home. What you're doing is you're filling this aquarium with water. So it says it is being filled with water at a rate of, you guys, if we're filling it with water, what's changing? Volume. So the rate that this gives me, even though it doesn't tell me volume, if you're filling this aquarium, that's dV dt. So dV dt is 200. You're filling it at a rate of 200 cubic centimeters. Okay, so what's happening is this. The water of this aquarium is basically going to be going up. Okay. Out of these 3 variables, 2 of these are actually fixed. They're not changing as you fill the tank. Do you know which 2 are fixed? The length and the width. So mark that these are fixed, and I'll show you why it's important. Fixed, fixed. What's changing is as you fill your tank with water, the height is changing. Okay, so this guy is not fixed. I'll show you why we need to understand what's fixed. Okay, so determine the rate at which the height of the water is rising. So what do they want? D what over D what? Determine the rate at which the height of the water is rising. Yep, so they want dH over dt. Okay, so this is what we're going to be looking for. Now we need a formula that's going to relate volume and height. So what would the formula be, first of all? The volume of a rectangular prism is what? Okay. Length times width times height. Now, once you have that formula that relates, so we've got the formula that relates volume and height. Some students would be like, okay, I'm going to differentiate both sides with respect to time, but we've got 3 different variables here, like uv prime. We can't do that. So if you have something fixed, it says create an equation. So here's our equation here. And then it says substitute only fixed or unchanging, which are our constant variables, into our formula. Because I can't take the derivative of this. I'm going to show you how in the next unit, what the formula for like v, uv, and then another variable would be, because there is one. But we don't know what it is right now. So we have some fixed variables that we could plug in at this stage. The fixed variables, the length doesn't change and the width doesn't change. So the volume is equal to, the length was 70, the width was 20, and then the height of this. Volume is equal to 7 times 2 is 14, and then 2 zeros, and then height. Now I've got my formula that relates volume. So now that I've input my fixed variables or my constants, we're going to differentiate both sides with respect to time. The derivative of v is 1, dv dt is equal to, what's the derivative of 1400h? Yes, 1400 dh over dt. Okay. From here, dv dt I know is 200. So I'm going to put in 200 is equal to 1400 dh over dt. And I could isolate dh dt, get it by itself by dividing both sides by 1400. So 200 over 1400. 2 zeros over 2 zeros will cancel. And then 2 goes into 2 once, and 2 goes into 14 7 times. So the rate at which the height is changing with respect to time is 1 over 7. Now let's figure out what the units would be. Do you know what the units would be for this? It's centimeters per minute. So here's two ways that we could think of this rate. The rate at which the height of the aquarium is changing with respect to time is 1 7 minute. Meter every 7 minutes is the two ways we could say that. Okay, let's do another one where there's something fixed. So we'll do the sphere last. This will be our last problem. Find this guy. A water tank has the shape of an upright cylinder. The cylinder is filling. Okay, so we're filling this cylinder at a rate of 1.3 meters cubed per minute. So we're filling the cylinder. So Maya, what did I just give you the rate of? Yes. So d what over d what? Yeah, dv over dt. This guy's filling at a rate of 1.5 meters cubed per minute. Yes, yes, yeah. If the tank has a radius of 200 centimeters, okay, we've got to be a little bit careful. My rate is in meters cubed. So when they give me the radius of this tank in centimeters, I want to convert that to meters. So because the rate is in meters, this would be the easier one to convert. So 200 centimeters is the radius. What would that be if 1 meter is equal to 100 centimeters? What would the radius of this cylinder be? Yes, 2 meters. Okay, so this cylinder has a radius of 2 meters. Okay, so that's the radius. At what rate is the water level increasing? So what rate is the water level increasing? Do you know what they're actually asking for? D what over D what? When they're asking for, like, what's happening is the water level is going up. Like it's increasing. So what would that be? D what over D what? DH. The height of this cylinder, as you fill it, the height's getting higher. So that's going to be DH over DT. So at what rate is that increasing when they want to know the rate once it gets to 320 centimeters? And that would be a height of 3.2 meters. Okay, so we need a formula that somehow relates volume to height. Okay, now I think in your note package I gave you this. So let's write what the volume of a cylinder is. Volume of a cylinder is pi r squared h. Okay, so you'll have your note package on the test, so you'll have all your formulas. So let's see if it relates those two. So volume of a cylinder is pi r squared h. Okay, so yes, I'm relating volume with height. I want to relate these two things, volume with height. Is there something fixed on this cylinder though that doesn't change no matter how much water you put into it? Yes, what's fixed? What did you say? The radius. This would be fixed. So this is fixed. You put in anything that's fixed or constant before you differentiate both sides with respect to time. So now I'm going to have the volume is equal to pi 2 squared times height. Volume is equal to 4 pi h. So now what we will do is we are going to differentiate both sides with respect to time. Derivative of v is 1 dv over dt. And then, does anybody know what the derivative of 4 pi h would be? It'd be 4 pi dh dt. Yeah. Derivative of 4 pi h would be 4 pi dh over dt. Okay, they gave me that the volume is 1.5, so I'm going to put the rate at which the volume is increasing. It's going up by 1.5 meters cubed every minute. I won't even put units for this. We'll do units at the end. Is equal to 4 pi dh over dt. We want to get dh by dt by itself. We don't have, and so sometimes this will throw students. They'll be like, I didn't have any place to put this 3.2 in. If there's no place to put it in, we're not putting it in, right? There's no place to put in when the height is equal to 3.2. So it doesn't go in. We just need to solve dh dt because that's what the question was asking for. So dh over dt is going to be 1.5 over 4 pi. It's height, so it's meters per, I believe, minute. And then you don't really want to have, like, if you could clean this up, you'd clean it up. What's 1.5 as a fraction? Do you remember what that would be? So it's 3 over 2. So let's see how we would clean this up. So 1.5 is equal to 3 over 2. So what we have is we have 3 over 2 divided by 4 pi. So what would it become? That would be 3 over 2. So here's my 3 over 2. And then instead of dividing it by 4 pi, I'm going to multiply it by 1 over 4 pi. So dh over dt, the rate at which the height is changing with respect to time, would be 3 over 8 pi. And then meters per minute. Okay. Let's do one last example. And that would be this guy. We have a snowball that's melting in such a way that the volume is decreasing at a rate of 1 centimeter cubed per minute. So Emily, tell me what you want me to write for this. Good. That's right. So we've got a snowball, big, huge snowball, let's pretend. It's melting at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing? So Owen, what do you want that to be? At what rate is the radius decreasing? Okay, so at what rate is a radius decreasing when, when the snowball is 5 centimeters. So we have big, huge snowball. Once it gets to a radius of 5 centimeters, at that particular moment in time, what was the rate at which the radius was decreasing with respect to time? Now, you guys, according to this, should we get a positive or negative rate for radius? A negative rate. The snowball is decreasing. The radius is getting smaller. Tomorrow I'll give you one, or later on, where you have a balloon that you're going to inflate. If I say, how does the rate of a balloon change? If you're inflating it, it would be a positive. This is going to be a negative number. Okay, so I need something with a formula with volume and radius. Abby, do you have what the volume of a sphere is? Okay, so I got that. And then I just look, I say, does it relate volume and radius? Yes, it does. Is there anything on a snowball when it melts that would be fixed? Think about it. Nothing. Nothing is fixed on a snowball melting, right? So this 5 will get input afterwards, like after I differentiate both sides with respect to time. That 3 will go in front. Oh, actually, sorry, let's do the derivative of v first. Derivative of v is dv over dt. And then 4/3 times 3, what would that be? It would just be 4. Yeah, because you'd have the 3 over the 3 would cancel. So it would be 4 pi r squared. And then I just took the derivative of r, so dr dt. So I implicitly derived both sides with respect to time. Now I could input the radius when it's 5. I'm able to input that now. So dv dt is -1 is equal to 4 pi. They want when the radius is 5. And then dr dt. I'm going to be dividing both sides by, what would this be? 5 squared is 25. 25 times 4 is 100. Do you guys agree that you divide it by 100 pi? So divide this side by 100 pi, divide this side by 100 pi, then that and that would cancel. So the rate at which the radius is changing with respect to time, the snowball is melting, so the radius is changing, it's going down. 1, so it's -1 over 100 pi, and it's radius, so it'd be centimeters per minute. And that's the rate at which it would be changing. Okay. For your homework, there are, I forget if it's 3 or 4 questions that you'd be doing. I think it's only 3 for this one. 1, 2, and 3 should already be done. So it says 4, 6. Okay, I guess we can't do 17. Let me see what 17b is, though. 159. Okay, you guys, this lesson you're only doing 3 questions. You're doing question 4, question 6, and then I want you to add 17b on page 159. It's a balloon being inflated, is what 17b is. On this page, 145, 17, I got to teach something in tomorrow's lesson for this guy. So again, just 4, 6, and 17b on 159.